Welcome back. This is another exciting episode of Mr. Takeda Teaches Algebra. I'm your host, Mr. Takeda, and I'm going to teach you some algebra right now. This is lesson 3.7 on absolute value functions. We've done linear functions, and now we'll do absolute value functions. They're closely related. And so let's take a look here. The essential question is, how do the values of A, H, and K, and what are A, H, and K? And in this case, A, H, and K are multiplying the output, adding or subtracting to the input, and then adding to the input. So we're transforming absolute value functions here. But let's take a look first at what an absolute value function is. An absolute value function, when we graph it, looks like this kind of V thing. This is the parent function. F of x equals the absolute value of x. So what does that mean? Well, if x is 1, y is 1. If x is 2, y is 2. If x is 3, y is 3. But if x is negative 1, the absolute value part of the function returns not a negative 1 for the y, but a positive 1 for the y. Negative 1, positive 1. Negative 2, positive 2. So we get this kind of V looking thing here. The vertex is this point here. We call this point the vertex, where the graph changes direction. We'll be using this term vertex for other types of functions as well. The domain is all real numbers, because all x's can be a part of the domain. But the range is y is greater than or equal to 0 for the parent function, because 0 is the lowest value we can have in the range. All y values are positive. That's for the parent function. Now, let's talk about transforming these here. I'm going to be using actually a graphing calculator online here to do this. We want to graph the parent function, and then we'll compare it to this. We're going to add 3 to the output. We'll add 3 to the output. So what's that going to look like? So here's the graphing calculator. It's called Desmos, D-E-S-M-O-S, if you see it up here, desmos.com. And it's a free online calculator, and we'll be using this a lot during the year. So here I've entered in the function for the parent function. F of x is just equal to the absolute value of x. And we want to add 3 to the output. So this is similar to what we did in the linear. Adding 3 to the output is just going to add 3 to all the y values. So what we're going to end up with here is a vertical shift upwards. So let's do this. Let me say let me see if this works. G of x is equal to, and then I'll just use the old notation here. The absolute value of x, so that's the same. Then I'm going to add 3 to that, plus 3. So you can see here that all the y values shifted up 3 spaces, 1, 2, 3 spaces up. Okay, so that's the vertical shift. Adding to the output's a vertical shift. All this is the same as from the linear. And the next thing we want to do is subtract 2 from the input. Subtract 2 from the input. And just like with the linear functions, let's see here. Was it 2? Subtract 2. Sorry. Subtracting 2. It does the opposite of what we think it's going to do. It actually moves it in the positive direction. This is the the horizontal shift, positive. We subtract 2 from the input. So the input is going to affect the horizontal shift. Adding or subtracting to the output is the vertical shift, up and down. Okay, so that's what these look like. Let's take a look at the next thing we want to do. Okay, again, we'll start with f of x equals x, but this time we'll multiply by a large number greater than 1 and then a fraction. And this is a negative fraction. So the negative number, I need you to think of this here, is really multiplying by what? Negative 1 times 1/2 times x. So we should know what a negative 1 multiplying by the negative 1 is going to do what? I'm going to ask you that, and I'm going to change screens. Okay, so there's the parent function again, and now we're going to put in, what do we call this, q of x, and we're going to do what? We're going to multiply the output by 2, right? So q of x equals 2 times the output. So this is our vertical stretch. We're stretching this. I can't really draw on here, but we're stretching this vertically, right? Every point here is now twice as high as it was. So if I had 1, 1, if I have 1, 1, now it's at 1, 2, because that the y value is twice as much as it was before. Maybe easier to see over here. At 5, 5, the corresponding point is now 5, 10. The y value is twice as much as it was. Okay, so let's take a look at the second function we want to put in here. That was p of x equals negative 1/2 times the absolute value of x. And where to go? There it is. Okay, so two things happened here. Let's do this. Let's do this in two parts so you can kind of see. The 1/2 here, we had the vertical stretch before. So now we have this horizontal shrink from this kind of red line. Now we're down here. What was 5, 5 is now 5, 2.5. It's half as much as it used to be. It's half as much as it used to be. But then by multiplying by that negative 1, I'm going to put that in here right now. If you look over here, I'll put that negative sign back in here. Now I've done that reflection across the x-axis. Okay, so a couple things are happening at the same time here. I'm doing that vertical shrink and then that reflection across the x-axis. Okay, and let me show you this as well. I want to show you just another type of notation here. Okay, so I've erased the old p of x. I'm going to put it back in, but this time instead of referring to the absolute value of x, watch this. I'm going to say negative 1/2. Now instead of saying absolute value of x, I'm going to refer to f of x because I've already up here defined the absolute value of x as the f of x, right? Or I should say that the other way around. I've defined f of x as the absolute value of x. So now down here, I can refer to f of x. So this is negative 1/2 f of x, and I get this graph, same as before. Okay, let's take a look at the next example we want to look at here. Oh, vertex form. This is because within the function itself, we can see the position of the vertex. Now remember, the position of the vertex in the parent function was at 0, 0. But when we look at the function here, where we're multiplying, and here we're subtracting h and adding k. Well, hk, since h moves us in a positive direction, even though we're subtracting it, moves at h spaces to the right. K, if it's positive, will move at k spaces up. HK will give us the new location of the vertex. Okay, and it'll be symmetric around the line x equals h. H will be kind of like the center line to the vertex. Okay, so get this vertex form idea in there. H and K will give us our new vertex. So we have graph f of x equals x plus 2 minus 3, and then we're going to compare these to each other, and g of x equals 2x plus 2 minus 3, and we're going to compare these. Okay, so let's go ahead and clear these out. And the first one was f of x equal to absolute value of x plus 2, and then minus 3 from the whole thing. So here we can see that our vertex is at -2, -3. It's the opposite of this. Remember, this is the one where it's backwards of what you think it's going to be. So it looks like it's adding 2, but it's really subtracting -2 and then subtracting 3. So our new vertex is down here. And the other graph we wanted to put in here, g of x, is equal to the absolute value of 2x plus 2, and then minus 3. Okay. So you'll see that this one is stretched. This one is stretched because we're multiplying the we're multiplying here. So it's actually a excuse me. It's horizontal shrink. We can think of graph G as a horizontal shrink of graph F by a factor of 1/2, because we have that 2 in there. So remember, it's the inverse. The y-intercept is the same for both graphs. Right here, you see the y-intercept is the same for both graphs. And the points on graph of F move halfway closer to the y-axis. That results in the graph of G. They're halfway closer. Right? They're moving down. When the input values of F are 2 times the input values of G, the output values of F and G are the same. Okay, so that's comparing just 2 graphs. We're just kind of talking about how things change, but I want you to see how this vertex form, we can see the 2 and the -3, but then the 2 here is changing it up. Last thing, we want to let g of x equal -2, multiplying that output of the absolute value of x minus 1, then add 3 to the output. Describe the transformations from the graph of f of x to the graph of g, then we'll graph it. Okay, well, I see -1, so I'm subtracting a +1. So my new vertex should be at 1, 3. And this -2, I'm going to have what? I'm going to have I'm reflecting over the x-axis. And then the 2, it's going to be a vertical stretch. So let's check those things out here real quick. And let me just make this one say, this is my parent function. And then my new function is going to be g of x equals -2, absolute value of x minus 1, and plus 3. Okay, so you see the vertical stretch. See, this is narrower than this one. It is reflected over, and then this vertex, well, what did we say the vertex was going to be? We said the new vertex would be at 1, 3. And we are here at 1, 3. So kind of imagine, let's do it in kind of steps here. There's our new vertex, right? We moved it 1 space this way and 3 spaces over, and then we reflected it and stretched it over the x-axis. Okay. So you can see a little bit better there. All righty. I believe that's it. Let's see. That's it. And that's the end of the lessons for Chapter 3. So we'll be going to review mode and quiz and test mode here in the next day or so. Thanks a lot, and have a great rest of your day.